Yeah.
I hope that's okay.
Yeah.
Thank you very much again.
Yeah.
Okay, then we come to the second talk, which will be given by Professor Raymond Pierre Humbert from the University of Oxford. Thank you very much. I also wanted to say this to Mr. Lama for accepting the invitation to give these talks. Professor Pierre Humbert's talk is entitled Geological Drivers of Habitability. Please, Ray, go ahead. We're looking forward to your presentation.
Yes, thank you very much. I'll just share my screen here. Yes, so this talk actually picks up on a number of themes that that Professor Lammer just spoke about. And the general theme of this talk is that habitability is at least as much a matter of geology as it is of atmospheric science or stellar properties and things of that sort. This is a subject that has become quite active in the last few years, probably really just in the last 5 years. So I'm not going to attempt to give a comprehensive overview of all the work going on in this fascinating, relatively new area. I will emphasize that almost all of it builds to some extent or another on pioneering early work by Jim Casting and by Walker and Hayes as well. So I will go through the basic picture of how the geology enters into habitability, and then talk about some specific work that's going on in my own group at Oxford. Now, there are many kinds of planets out there, and this talk will only deal with one particular class of planets, which is not exactly a clone of Earth, but it engages the same habitability maintenance mechanisms that the Earth has kept the Earth habitable, with a few interruptions over 4 or so billions of years. So we deal with a planet that it might or might not have an iron core, but the important thing is that most of the planet has a rocky composition with a silicate mantle that is overlain by a fairly thin ocean and atmosphere, water ocean and atmosphere, not talking about CO2 oceans or methane oceans or anything like that. And when I say thin, I mean that the ocean and atmosphere have a small mass compared to the total mass of the planet. Now, there are various variations on the theme. You might or might not have continents, that continental material that sticks up above the ocean. You might have ice, low pressure ice 1, forming on land and also forming in the freezable ocean water in some places, like the Earth has. If your ocean is deep enough, you might have a layer of high pressure ice 6 or ice 7, at the bottom of the ocean simultaneously, which has the possibility of interfering with the contact of the silicate mantle with the atmosphere and volatile exchange. Now, there are many other potentially habitable types of planets out there, including things like cloud life on sub-Neptunes and so forth. But I'm going to confine attention to this one particular problem, which is really rich enough. Okay. Now, habitability is contingent on planets having the right kind of atmosphere. And so while there are many kinds of atmospheres that could support habitability in the sense of liquid water at the surface, many greenhouse gases, I'm going to consider the carbon dioxide water vapor family of atmospheres, which is basically what has maintained the habitability of the Earth, and it's what went wrong on Venus that led Venus to be too hot to be habitable. You can add N2 without substantially changing the picture that I'm giving here. But I should emphasize that although I won't talk about N2 in this talk, N2 is absolutely essential for the chemistry of life as we know it. We can't say anything about N2 in life as we don't know it at present. But for anything like Earth-like biology, N2 is an essential ingredient. Again, there are many other kinds of atmospheres that could support liquid water habitability or destroy it, but I will confine myself to the CO2 water system. Now, just to review the conventional definition of the liquid water habitable zone, some people say it should be called the hunting zone because being in the habitable zone doesn't by any means guarantee habitability. You need the right kind of atmosphere, and you need to be able to maintain the right kind of atmosphere in order to be habitable. And here's your star. And so the inner edge of the habitable. Oh, let me get my my pointer so that shows up better. Yeah. So there's your star. And the inner edge of the habitable zone is determined by the H2O runaway greenhouse, in which circumstances you probably have low carbon dioxide on the atmosphere. And the properties of the inner edge are dominated by the properties of the thermodynamic and radiative properties of water vapor. The outer edge of the habitable zone is a bit more complicated, but out there, although water vapor still can play a role in maintaining the greenhouse effect as a feedback, the limits on the outer edge of the habitable zone for this class of planets that I'm discussing are determined by a combination, a sort of interaction of CO2 condensation in the atmosphere and the maximum greenhouse effect. You have, which I will explain in the next slide. And you tend to have a CO2 dominated condition at the outer edge of the habitable zone. So here are some calculations, so it's sort of a riff on the work on habitable zones by Jim Casting and followers. Here's some calculations done by my student R.J. Graham with the Socrates radiation model. The horizontal axis is the CO2 partial pressure. And we also have water vapor supplied by an ocean that keeps the atmosphere saturated. So this water vapor is a feedback in this, but these are all CO2 dominated atmospheres, except for maybe the hottest ones. So the middle graph is like the analog of sigma t to the fourth. This is the rate of cooling to space in watts per square meter. As the planet gets hotter, you radiate more. As you put more CO2 in the atmosphere, you radiate less. So this is going from 1 bar to 50 bars. But as Jim Casting noted, when you put more CO2 in the atmosphere, you increase the albedo, and that works against the greenhouse effect. And the top plot puts both effects together. This is the temperature between 250 Kelvin to 350 Kelvin here. It tells you the installation, the amount of stellar radiation, the incident on the planet relative to the Earth. Earth would be 1, Earth installation would be 1 on this, with this measure. Tells you the installation needed to maintain a given temperature for a given amount of CO2. And so you can, so the top graph is the main one, the top plot is the main one to look at. And so this just points out that the habitability, even for this CO2 water system, is contingent on how much CO2 there is in the atmosphere. And so if we had 1 bar of CO2 in the atmosphere, even if you're only getting 3/4 of the installation that Earth gets, so it's sort of farther out from its star relative to the star than the Earth is. If you had a bar in the atmosphere, a bar of CO2, you have temperatures in excess of 350 Kelvin, where it becomes uninhabitable even for most extremophiles. And then if you had Earth-like installation, your temperatures would be up where you would really destroy, denature essentially all forms of proteins that we know about. But similarly, if you're farther out in the habitable zone, this is out where in this blue band where you're getting about 50% of the installation of the incident stellar radiation as Earth. If you only had 2 bars of CO2 in the atmosphere, reading out the 2 there, then your temperature would be hovering around freezing, at which point with isoalbedo feedback, you would kick over into a snowball and be completely frozen over. And with less CO2, it's even worse. So without enough CO2, it's too cold. And then on the other hand, if you take the same installation but you give it about 10 bars of CO2, you wind up with temperatures about 280 Kelvin, which is in the just right zone. You do have a Goldilocks planet. So the upshot is that determining the habitability requires an understanding of CO2 sources and sinks. And this is something that this is oh my. Yeah, this is something that has been studied for the Earth for quite a long time. It actually even goes back to very early work on silicate weathering, on metallic weathering by Ebbelman, and has continued without interruption over the years, but it remains an extremely challenging problem. But so determining habitability requires an understanding of carbon dioxide sources and sinks. And at Oxford, we've been working on both ends of this problem. So this is the model of the deep carbon cycle on the class of planets I've spoken about that ultimately determines the content of CO2, carbon dioxide in the atmosphere. There's a sink of carbon dioxide if you have rain reaching the crust, and if the crust is made out of silicate rocks, like rocks with the SiO3 ion in them, or relatives of that particular form of silicate. So the silicon and oxygen hooked to some sort of metal, calcium silicate, magnesium silicate, and so forth. Many common rocks like feldspar basalt are silicate rocks. So if in the presence of liquid water, CO2 reacts with silicate rocks to make carbonates, and that's a sink of CO2, which depends on all sorts of chemical properties and physical properties at the surface. And so that would remove all the CO2 from the atmosphere until you froze over, unless it was compensated by outgassing. So the outgassing is equally important. And that's maintained by either resurfacing by volcanism, which pushes the carbonates down to where they can decompose at high pressures, high temperatures, or by plate tectonics, which subducts the ocean floor slabs, which bear carbonate, and heats them up to the point where either after they've made a trip through the deep mantle and come back up, or through in situ melting, melt and then release carbon dioxide back into the atmosphere in the form of various kinds of volcanism. But to keep this process going, you need a heat source in the silicate mantle. And the main heat source for the Earth, and probably most planets, a large class of planets, is from fission, radiogenic heating from long-lived radioisotopes. And Professor Lammer already brought these in. The two that to keep your eye on most are thorium-232 and uranium-238, which are very long-lived. But potassium-40, although it's much shorter lived than the other two, is still important at present on Earth because there's so much of it. But a silicate mantle heat source is absolutely crucial. It maintains the mantle convection. The mantle stirring is necessary to sustain volcanic outgassing. The mantle stirring is also necessary for all known means of recycling crustal carbonates. And the heat source can be provided by decay of long-lived radionuclides, but for close-in rocky planets, especially around M-stars, tidal heating could also be a factor. And I won't have any time to talk about the possibility of tidal heating. But just to give you an idea of our situation on Earth, and there's nothing magical about the amount of uranium and thorium the Earth has. This could be very different for other planets. This is 4.5 billion years ago. This is the present. Most of the U-235 has decayed away. But the thorium is still heating the Earth about as much as it did in the beginning, and U-238 hasn't decayed all that much. Potassium-40 has decayed quite a lot, but it's still giving us about about a third of the total heating. But the proportion of all of these things could be quite different. And as Professor Lambert just pointed out, you can lose potassium-40 in the early stages of a planetary evolution, which could actually cause the planet to cool down substantially faster than the Earth did. Now, U-238, the R process elements come from rather exotic astrophysical events. It used to be thought that they were mainly made in supernovae, but recent result pushes things in the direction of saying that even more exotic and infrequent events are responsible for most of the R process elements, including these. So you have merging neutron stars and also collapsars. There's a collapsar, there's a merged neutron star. And the source of all these things depends on the rate of formation of massive stars. And the long half-life, especially of U-238 and thorium-232, means that there is enough time for these things to mix throughout a galaxy. But given that these are infrequent events, there's the question of just how homogeneous are uranium and thorium in the galaxy. Some planets may not have been lucky enough to be near a collapsar, and the uranium and thorium are just too dilute, so they don't get much of it in their protoplanetary disk. And also, elliptical galaxies, unlike spiral arm galaxies like our own, have a lower rate of formation of stars and more stars trapped in low mass, more material trapped in low mass stars. So we don't expect them to generate as much uranium and thorium and long-lived habitable planets. Okay, now let's get to the sink. We'll talk about the sink, and I have to go through this rather quickly because we don't have much time. But in my group, we've been exploring the effects of new models of silicate weathering, the CO2 sink, due to Mayer and Chamberlain. We call it MAC for short. And there's a paper where you can read about some of the effects of this on habitability. But the general idea in the Mayer and Chamberlain formulation is that there are actually two different regimes of weathering. One is kinetic limited, where the flow rate over silicate rock, whether it's on the seafloor or on continents, is so fast that the actual kinetics of the dissolution of silicate controls the rate of weathering and formation of carbonate. But if the reaction rate is fast, or if the flow is slow, instead, there's time for the silicate concentration to reach in dissolved silicate in the liquid to reach equilibrium, in which case you actually lose the Arrhenius kinetic temperature dependence, and it becomes almost entirely dependent on just the flow rate. And the flow rate is sensitive to temperature to some extent, but in a different way than the Arrhenius kinetics. So this is the formula from Mayer and Chamberlain. The W is the weathering rate, Q is the runoff rate, the flow over the reacting silicate. CEQ is the equilibrium constant for the silicate dissolution reaction, and D sub W is a Damcolor coefficient. D sub W over Q is the Damcolor coefficient number, which gives the reaction rate versus the flow time. And so in the kinetic limit, this reduces to just CEQ times the Damcolor coefficient. CEQ has very little temperature dependence. It's mostly dependent on pH, which CO2 affects. But D sub W does have an Arrhenius temperature dependence. It exponentially increases with temperature, as long as the temperature doesn't get too large. But in the equilibrium limit, you lose the Damcolor coefficient, and it's just the flow rate times CEQ, which has very little temperature dependence. So the only temperature feedback in the system comes from the temperature dependence of the runoff. Warm atmospheres having more precipitation, generally up to a point when you reach energetic limits that are discussed in the paper I cited on the previous slide. I just contrast that with the classic formulation, which most exoplanet habitability studies are based on, the Walker-Hayes and Casting formulation, which always has an Arrhenius temperature dependence in addition to an explicit dependence on carbon dioxide. So the Mayer and Chamberlain formulation gets you much closer to the actual physical chemistry of weathering. Now, weathering also occurs on the seafloor. The ocean crust is silicate. There's no shortage of water, and dissolved CO2 can react with the crust with which it comes into contact. This was ignored for a long time, but it's now being recognized that seafloor weathering is an important part of the story, at least for some kinds of planets, especially for planets that have very little continental area. The carbonates can form on the seafloor, but the controls on the rate are poorly understood. And suffice it to say here that in the simulations I'm going to show you, we make use of a very simplified form of the MAC kinetic versus equilibrium weathering formula with some assumptions about hydrothermal flow through the pore space in seafloor basalts to get a placeholder model of seafloor weathering, because you can't ignore it. Now, the weathering model contains many coefficients that may differ from values on Earth and can't be directly inferred for exoplanets. Crustal mineralogy, the rate of formation of regolith or reaction surface area, and seafloor hydrothermal parameters. But the first task of a comprehensive habitability model is to put plausible bounds on the range of values and explore the sensitivity. Now, the sources of CO2 on the long term come from recycling of crustal carbonates, and CO2 is liberated where mantle or crustal minerals melt in the standard current view. Melting is favored by high temperature, suppressed by high pressure. The rate of melt production increases with the strength of mantle convection. This is basically the same process. That makes cement when you cook limestone to make calcium oxide, quicklime, and then release CO2 in the process. For example, magnesite, which is one of the main bearers of carbon in the upper mantle, melts and releases CO2, makes magnesium oxide, which eventually turns into new silicate rocks. This is a cartoon from Dasgupta et al. I recommend reading this paper, just pointing out that the melt that releases CO2 is mostly happening in the upper 300 kilometers or so of the mantle. You get some outgassing of CO2 where plates are subducted and you release that in arc volcanism. Some carbonate escapes into the deep mantle where on a timescale of 1 billion years or so, it gets recycled either through ocean island volcanism like Hawaii or Iceland, or the mid-ocean ridge where you are forming new oceanic plates. Okay. I'm running out of time, so I want to show you just two slides from some of our coupled model results. We put together a very highly idealized coupled model of all these processes knit together by a simple atmospheric energy balance model. And here is one example. This is the effect of the planetary radius and the content of the long-lived radionuclides. The radius for these first two cases is Earth radius. The radius for the first case and the third case is the Earth radius. The others are for twice the Earth radius. And the first two curves are for an Earth-like proportion of radiogenic nuclides. And the second two are what happens when you have only 1/10 the amount. You can see that a big planet, and this shaded area is where the planets basically gets frozen over. You can see that actually with a big planet for Earth-like radionuclides, you actually maintain habitability for 40 gigayears. So that's longer than the main sequence lifetime of a G star like the sun, but not of an M star. But if you have a small planet with 1/10 as much radionuclides, then you actually start to bump up against the main sequence lifetime of even a G star. And then if you go further out in that, this is for an Earth-like position in the habitable zone, like near the inner edge. If you go farther out, your habitability time is even more contingent. On the weathering processes. So this is now the age of the universe. So these are things that are happening right now in our universe on some planets, and these subsequent successive curves show what happens as you go farther out in the habitable zone down to where you have 80% of Earth's installation, where you can contract the habitable time for an Earth-sized planet, even with Earth-like radiogenic content to just 1 billion years. So this is actually important not just for the future of the universe, but it's important right now if you go farther out in the habitable zone. I wouldn't have time to talk about magma oceans. I'm out of time. I will just mention that they set the initial conditions both in the atmosphere and in the mantle for subsequent evolution. And I do want to plug 2 recent papers from my group by Tim Lichtenberg and coworkers, and by Ryan Brucrush and coworkers that bear on some aspects of magma oceans. So finally, tectonic freeze-out severely limits the habitability time, especially when you're at the outer half of the nominal habitable zone. There's a need to explore the effect of alternate mineralogies and so forth on CO2 sources and sinks. These results will all assume efficient crustal recycling. For inefficient recycling, the tectonic freeze-out could be an even more severe limit to the habitable zone, even near the inner edge of the habitable zone for G stars. The supply of long-lived radionuclides is crucial to habitability, maintaining habitabilities. And NSARs may well live 1 trillion years or more on the main sequence, but their planets will freeze out after 100 billion years or less, barring technological intervention. So that they don't have unlimited time to develop life out in the long future of the universe. But there are a number of questions outstanding. What are the plausible ranges of uncertain weathering and outgassing parameters? The behavior of seafloor weathering crucially needs to be better understood. How can we use astronomical observations to test climate regulation theories? This requires first detecting CO2 in a catalog of rocky exoplanets, and then characterizing its mixing ratio. But then the toughest thing of all, which is essential, is characterizing its partial pressure at the surface, or the column inventory of carbon dioxide. And that's going to be quite a challenge, especially for thick atmospheres. And finally, Earth and Venus are very depleted in carbon relative to solar composition. Is this typical? Where did our carbon go? Is it in the core? Is it someplace else? And if a planet starts off with too much carbon, can ingassing render it habitable, or does it remain too hot forever, even if it's in the habitable zone? So I think I will stop there and allow so that we have time for just a few questions.
Okay, thanks a lot for this very interesting talk, Professor Pierre Humbert. Yeah, we have time for a few questions. You can type questions in the chat or in the F&A chat window, or you can also raise your hand to ask a question. Are there any questions? Now would be the time to ask questions. Maybe I can ask a fairly simple question. You also explained possible CO2 sources, outgassing sources. Is it known to what extent the different rock types contribute or have contributed to the CO2 that was outgassed?
There's a question of where did the first CO2 come from to begin with. But at least for the Earth, all the CO2 sources that come from the interior of a rocky planet, they come from the decomposition. They come from the decomposition of carbonate rocks of various sorts. But when those rocks get into the deep mantle, they often don't stay as carbonates. You can actually turn them into various other forms, iron carbides and things like that. And then they actually have to sort of get reoxidized into carbonates when they go higher up in a process often called redox melting. And so there's a variety of rock types involved, but so far as we know, it's one form or another of carbonate. And it's actually magnesite or magnesium carbonate that's probably the dominant rock that directly leads to outgassing on Earth. But other forms of carbonate could be present in the mantles of other planets, for instance, super Earths, which have different pressure temperature regimes than the Earth's interior does.
Okay, thank you. Now we have two questions. Thomas Leisner, please go ahead. I guess you can just switch on your microphone.
Yeah, hello everybody. Hope you can hear me now. Ray, yes. It was a great talk.
Oh yes, I hear you, yes. Yep.
I was wondering, you showed that it's quite involved and tricky to keep carbon dioxide stable over long periods of time because radioactivity is declining and maybe magma is slowing down. So couldn't you think of a planet that is completely burned out, so to say, no recycling anymore? All the carbon dioxide is weathered away in carbonates, but it's in the right distance from its star and has a nice and life going on it because it doesn't need carbon dioxide at all.
Oh well, I guess if the planet had water in it. The problem is that that if you have liquid water, you will generally need some some carbon dioxide to keep enough water vapor in the atmosphere to give you a greenhouse effect. But I guess
if you're a little bit closer to the sun,
yeah,
then maybe you don't need to.
Well, so if it were exactly, you could imagine a planet that maintained its greenhouse effect just by water vapor with a nitrogen background atmosphere. But the position of the planet has to be really carefully tuned in that case. In order to be habitable, and for a G star, or which has stellar evolution, which brightens over time, you still have a limited habitability time, because if it's habitable in the early days, it will go into a runaway greenhouse in the later days. But for an M star, which doesn't evolve very much, you do have the possibility, if your planet is just exactly tuned right, if it's in exactly the right place, you do have the possibility of habitability that is just maintained by the water vapor that has evaporated from the ocean.
Okay, maybe we can take one last question. There was one by Lee Grenfell.
Hey, can you hear me?
Yes, yeah,
yes,
we can hear you.
Yes.
Hi, Ray. Thanks for a great talk. Just quickly, you mentioned, you touched upon towards the end of your talk about the possibility of constraining observationally mantle compositions. There've been a couple of speculative papers, like by Renyu Hu, about whether we can distinguish granitoids from silicates. Could you comment maybe a little bit on, could we do anything at all with for your variant carbon content mantles?
Well, yes, actually, I mean, the Hu paper, if it's the one that just recently was accepted in AppJ, that paper doesn't actually discuss silicate weathering at all. That actually makes the incorrect claim that the atmospheric carbon dioxide content is purely determined by the pH of the ocean.
Well, I meant an earlier paper 3 or 4 years ago. I didn't know about a new one, but anyway. Okay. Yeah.
Well, all of the techniques for trying to test the silicate weathering ideas do involve some kind of detection of carbon dioxide. And so this is an emerging area. You can try to detect it by albedo. You can try and detect it by its infrared fingerprint, things like that. But the tricky thing is that it's not enough to just detect carbon dioxide. To really test weathering, you need to know what the column abundance of the carbon dioxide is. And that's going to be a very challenging observation. What a lot of the earlier papers, including that one by Renyu that you were mentioning, a lot of those earlier papers are based on a kind of an oversimplistic picture of what controls there are on the amount of silicate weathering, which just tend to do things like look for a general trend in CO2 versus distance from the star. And there are so many other things that go into both the sources and the sinks that's not actually going to likely to be the test of whether the weathering works. We'll need other ways of interpreting this very diverse behavior of the deep carbon cycle in order to make sense of the kind of data, even once we've got it. But the first order of business is just to detect carbon dioxide at all on rocky planets, which hasn't really been done yet. But with James Webb, that starts to become possible.
Thank you.
Okay, thank you very much. I'm sorry, but we have to stop it here. Any further questions will have to be asked via the chat or via email. Thanks again. And I'm now handing over to Thomas Wiegelmann.
So thank you very much.